Hi, my name is Jacob Bender. I am your guest lecturer today regarding load computations. This is the second in a series of 3 videos. This video is talking about cooling load calculations. For expediency, I am assuming that you have already watched the heating load calculations one. There are several concepts that are the same between the two that I'm going to gloss over on this particular lecture. So if you're feeling particularly lost, it'd probably be a good idea to go back and rewatch the parts of the previous video. As a recap, heat's flowing, always flows from an area of high temperature to an area of low temperature. Insulation provides a buffer between the two. On the heating load calcs, the area of high temperature is inside the building. For cooling load calcs, the area of high temperature is outside the building. We want to be able to calculate that rate of heat gain inside the building so we can design a system that will remove excess heat in the space in order to maintain the desired temperature. Very much like the heating load calcs, heating gain factors come in from transmission, infiltration, and ventilation. However, we also are taking into account solar gains and internal gains in the space a little more intensely here. Whereas on the heating load side, those heat generating devices inside the building is actually a benefit to the overall system. Here it doubles down working against us for our overall load calculations. Typically, again, we're dealing with IP, US customary units in BTUs, same equation, Q equals UA delta T in play with this as well. The solar gains that we need to worry about when light is shining on objects through a window in the space, much like the Earth absorbs and re-emits heat, those objects inside the space will absorb solar energy and disperse it back into the space. Internal loads, in this case, will generate the same with lights and heat and kitchen equipment. But for that and ventilation infiltration, we're no longer just worried about our dry bulb changes back and forth. We now have dry bulb and wet bulb conditions to address. For our calculation methods, same as heating load calcs, there's a variety of options that range from rules of thumb to complex modeling. There's a list of between 6 and 8 different modeling methods that's listed in your textbook chapter that you can go in and read through. I'm not going to go over each one in depth right now. We'll touch on a little bit of at least one of those methods in the third video when we go over some example problems. Our design conditions are going to be arranged around peak summer conditions. We end up using tabulated historical data that's based geographically to figure out the worst case scenarios that a particular area has experienced so far and be able to design accordingly. Our total cooling is made up of both sensible cooling and latent loading. The sensible heat is your basic temperature change, bringing the space from one higher temperature to a lower temperature. The latent is actually what's dealing with moisture and humidity. Your latent loads are removed in the HVAC unit as your air passes across the cooling coils. The moisture in the air condenses and gets removed from the overall system. The longer that you have air moving across those coils, the more moisture gets wrung out of it. If your unit takes care of the sensible component of that very quickly, it may not have long enough for that unit to run and actually get moisture out of the air, and you're left with a cold and humid space, which is very uncomfortable for people inside as well. When a unit is oversized, it can have a tendency to take care of that sensible load too fast and leave that latent in the space. This is called short cycling and is a big problem with oversizing of your HVAC equipment. In sizing HVAC equipment, you're dealing with everything sized in a concept called tons. 1 ton of cooling is actually about 12,000 BTUs of cooling overall. And that 12,000 BTUs is broken down into both your sensible and latent components. Now, it's not an equal split, and it's not very variable between the two. Of a given ton of cooling, that 12,000 BTUs, you're looking at probably about 75% of that being your sensible capacity and 25% being your latent capacity. Your textbook mentions that the ideal situation for your loading on space is the latent load being less than 30% of overall. However, real world circumstances, we can see some far worse splits in that instance. I've seen some kitchen areas or similar areas that are at maybe a 50-50 split. So you need to be aware of that when you're specifying units and helping to pick them out. When you have an unfavorable split like that, you're going to want to take into account some options with your HVAC equipment to better deal with humidity needs inside the space. There are a few options that do help address that issue. Variable speed fans and VRF are two things that are becoming far more common nowadays. Variable speed fans can be used in conjunction with controls to slow down the airspeed and quantity of air moving through. Like I said, the longer that air spends moving over the coil, the more moisture is wrung out. If it speeds or slows down the amount of air that's flowing across it, it spends longer in the system overall and can address that a little more quickly. VRF units are technology has come out in the last they've become more prevalent the last 5 to 10 years, and those modulate their actual capacity to fit the needs of the space as it's needed. Humidity controls inside the space help to make sure that your HVAC unit and your controls logic knows that there is humidity in the space, even if your temperature is taken care of. In conjunction with that, you may specify reheat, which allows the unit to run and function and wring out moisture even if this space and sensible loads are met. It'll bring in air, cool it down to get that moisture out, and then reheat it back to room temperature so you're not noticing a change in the discharge temperature at each of your outlets. Or your HVAC equipment may function with multiple stage cooling. 7.5 ton unit may be staged with a 2.5 ton first stage and 5 ton second stage. And if there's a humidity problem in the space, it can run for longer at the lower capacity end of that until the latent need is met before kicking on the full capacity and taking care of sensible and before shutting off. Those can be built in as a solid 1 stage, 2 stage with a set tonnage between the two. There are also some accessories on the market now that allow simulation of that modulating capacity, even on older units that may be reused. They can be installed in the field as an afterthought. When tabulating our overall heat loss on the building, or heat gain on the building, it's basically the same method as heat loss. Your transmission is going to go through the same process of figuring out your U value, your area, and your delta T and calculating that. And you're going to add in the calculated values for your ventilation and infiltration and your various gains and losses from individual components inside the space. Since there's such a variation from all factors, you assume that all the peaks happen at the same time, but in real life, your peak sensible loading and your peak latent loading may not occur at the same time. So you got to make sure that your system has a versatility that it's able to address changing circumstances through each day. The estimation methods for the amount of cooling that is done is basically the same here as what we'd addressed in the heat loss and heat loads calculations. We've got the degree day, bin energy, and hour by hour simulations. These utilize the EER values, which is the energy efficiency ratio that measure the unit effectiveness. and how much energy goes into play with it. You also have cooling load hours, where you're estimating the number of hours a day that the cooling system is going to be running, and factor that into the number of days of operation and how much power each one's consuming to figure out your operating costs. Your typical units are pretty much all operating on the same fundamental properties and principles. The big differences that come into play between your different types of units is your coolant type and your compressor design. Two primary versions of coolant. You do have boiler and chiller systems that utilize water as the primary refrigerant flowing back and forth. Those have a boiler typically located in a basement and a chiller on a roof, and it circulates hot and cold water lines through the building and uses those for your heating and cooling loads between everything in the building. For other systems that are called DX or unitary, those are what uses industrial refrigerants. Probably familiar with R32A from cars, or R134, sorry. R32A is an outdated version of refrigerant for HVAC systems. Current going refrigerant is R44A, and those are very efficient, but they're also hazardous if there's too much refrigerant in a space. If they escape in gaseous form and there's too much of it in a high concentration inside a building, then it could be potentially hazardous to the occupants of that space. So we run calculations to make sure that the units specified aren't overbearing on that. And then our compressors, standard is just a single stage compressor at a set value. The multi-stage, like I mentioned earlier with humidity, is staggering that and giving you options for loading through the future. And then scroll compressors are a modulating compressor that allows it to vary the capacity in and out on a case-by-case basis. We'll touch on a little bit more with the cooling calculations and our example problems, but this does it for our main lecture on cooling load calculations. If you have any questions, reach out to Crystal, and I'm going to give her my contact information. If you have some fundamental questions, feel free to reach out to me, and I will do my best to answer them in effective means. Thank you very much.